So what I'm going to be doing is I'm going to be making a binary watch. This is my old watch design. It had LEDs and then they would spin around. In my newer design, I thought I'm going to make it count in binary. And normally in binary you have a kind of table, and each LED you would have seconds, minutes, hours, and the seconds would count using the binary table. You have minutes and hours. But I think I'm going to change the design. Instead of having it horizontal, this is like the normal way that you would draw it. But I think I'm going to flip it and make the columns, the seconds kind of counting up in columns. Because on a watch, I have some addressable LEDs, and they can kind of go more vertical. So if you have 3 strips vertical, you can count the time. So that's what I'm going to be doing.
The first thing that I did was I used KiCad to design the binary watch. And then after I had the circuitry, I sent it to JLPCB and they were able to sponsor this project. And I really liked their website where you can just upload your Gerber files and it'll automatically detect all the different layers, and you can choose the different thickness, the different silk color. It's just really user friendly. And they also offer PCB assembly. And I thought that's really cool too, because if you have a bill of materials and the parts, it will automatically place and sort the different components. So you could actually get it delivered with the parts on your board. So I thought that was pretty cool. And they also offer some flexible printed circuit boards as well. And this is really good for thermal as well, or if you want to make some LED strips that are flexible, you could kind of make a design that's flexible as well.
So my binary watch just came in the mail here. So I'll just open up and have a look at it. Came quite fast, delivered right to the door. What it looks like, the binary watch. Oh, they have this little logo there. I don't really particularly like that. I guess it'll be covered with the band, but it's gonna go on my arm here. That's the LEDs, and on the flip side we have our microprocessor here, charging circuit, and then the timer keeper there. It's gonna have 2 switches, so I'm gonna be assembling that. That's the board. And here's all the other individual parts that I ordered so that we can start putting on, like the LEDs, and have a pack of surface mount resistors. And I have this kind of liquid solder that just uses a heat gun to put everything onto the board. I think it's, let's see here, like 180 degrees and it'll liquefy. So that's what I'm going to be using to put on the stuff.
And so just using the heat gun, I put all the components on, and then it will just self solder basically. And then we actually have the board that we can just program. So this is after I assembled it and uploaded the code. I put the code in the description. You can see you have your seconds, minutes, and hours. If you hold the bottom right button, that is going to go into the changing the time mode. The top button is to increment that. So this is incrementing the seconds. And then you can increment the minutes and hours like that. And when you're done fixing the time, you just hold the bottom button and then it's in the normal mode. If you hold the top button for 1 second, it will go into standby mode. And I programmed it so after about a minute, it will self turn off. And if you push both buttons at the same time, that's going to increment the brightness. So if you're outside, then you can still see it. Or at night, it has lower power. So it has 2 surface mount push buttons there. It has USB-C charging there, and it has a 200 milliamp hour LiPo battery, and it's just using the TP 4056 charger IC for the LiPo battery, and that's this place right here where you have your diodes for to show that it's that. And at the very top, you'll notice you're not going to have 32 hours, but if it turns blue, that means that it's a low power, and then you can just charge it. Now, an interesting thing about this design is you can program it using the serial, the USB to serial chip, which is it's a C3040, CH3040 chip, and when you plug it in, it can detect it. And because it's connected to this chip right here, and that's to go into USB to serial. And normally they tie the positive, the D positive and negatives. There's actually two versions, but in this unique design, I split the lines there because I wanted the SPI pins to connect to my USB port, because usually you have header pins to program it. And so when you plug it in, the one way is connecting to the A pins, and that's so that we can use the USB to serial chip. But if I flip it all the way around the other side, it doesn't detect, is because then I can use a header pin. I can just use a wire to connect to my USB port, because I've routed out the SPI pins right to the chip there, so I can use my USB port to also program using the SPI. So that's nifty. Now, when I actually tested the current in standby, it was using 15 milliamps, and that's a little high because I'm thinking that these 5 millimeter addressable LEDs are using some current in standby mode. So I'm thinking that I'm going to have to isolate that. And also I can, in the future, I'm thinking about this bootloading 8 internal megahertz bootloader, so that I don't have to use the resonator there, because I do have everything isolated using a Schottky diode for the USB to serial chip and also the charger chip, and I'm only using the DS3231 timer chip right to the battery. So I'm not too sure why it's using so much current, but in the future I'm going to be upgrading this as well. If you have any comments or ideas or suggestions for this, give a comment, and I'll see you in the next video. Thanks to JLPCB for providing the printed circuit boards, and I also left a description about a coupon that you can get 5 boards for $2, and you get $10 off your first orders.